Hello everyone and welcome back. Today I wanted to make a video that clarified the differences between mass and weight. And the reason for that being is that in our everyday language, these two are used pretty interchangeably. However, in physics, knowing the difference between these two is actually very important. So today we're going to talk about those differences and I'm going to show you how you can work with each of these. To start out, let's define them both. So what is mass? Mass, simply defined, is the amount of matter in an object, literally the amount of stuff inside you or in any object. Okay, then, what is weight? Well, weight is the amount of force the planet pulls on an object with. So when we say our weight, it is literally how much Earth is pulling on us. Your mass is a representation of how much matter is inside you. Your weight is a representation of how much the planet you are standing on is pulling on you with. If you were to be teleported to the moon somehow, your mass would not change. The amount of matter in your body would not be any different. However, your weight would change. Your weight on the moon would be about 1/6 of what it is on Earth. So, the fact that I can change one of these without changing the other means that these two fundamentally are not the same thing. So, mass and weight are related, but they are not the same thing. There's a good deal of confusion due to some of the ways these are used in our society. For example, if you go to the gym and lift up the barbells, on the side of the barbell, it will give two numbers. One number will be in kilograms, which is its mass. The other will be in pounds, which is its weight. So a lot of people look at that and think they are the same thing. However, if you were to take that barbell and again bring it to the moon, one of those numbers would still be correct and the other one would be very, very wrong. Another thing to note is there are a lot of countries where if you ask someone their weight, they will give you their weight in kilograms. However, technically, they're not giving you their weight, they're giving you their mass. But that is simply how the language is spoken in that society. So let's take a little of what we just said and talk about how you would actually use it in the physics classroom. Let's say I have this man, and his mass is 70 kilograms. 70 kilograms is about the average mass for an adult male. Let's say this person is on Earth. Here's the Earth. Now, you live on the surface of the Earth, and unless you're going to be an astronaut in the future, you are never going to leave the surface of the Earth. Now, there's one more misconception that I want to actually try and kill today, and that is the idea that there is a conversion between pounds and kilograms. There is no such thing. Pounds is a measurement of force, and kilograms is a measurement of mass. These are not the same thing. However, there is an equation that can be used to translate between one and the other as long as you know what planet you're on. In our case, the assumption is we're on planet Earth because 99.999% of us will actually never leave its surface. So I'm going to take my man here, I'm going to put him on the surface of the Earth, which means the Earth, no matter where I put him, the Earth is going to pull him toward its center. So from our point of view, that direction is always down. Now, if you're standing on the surface of the Earth will pull on you with a certain amount of force depending on how much mass you have. And that value is about 9.8 newtons per kilogram. So for every kilogram of mass that you have, the Earth will pull on you with 9.8 newtons of force. This value is so commonly used that it has its own label, and the label is a lowercase g. If you were on the moon, I'll put GM for moon, is about 1.6 newtons per kilogram. So let's take our man who has a mass of 70 kilograms and let's find out how much he weighs. How much he weighs by definition is how much force Earth pulls on him with. Well, with this relationship, I could actually rewrite this like this. Force Earth on object is mass times g, where g is how much force Earth pulls an object per kilogram as long as you're standing on its surface. So force Earth on, say this is Bob, force Earth on Bob would be his mass, 70 kilograms, times G, which is 9.8 newtons per kilogram. My kilograms cancel, and I get a weight of 686 newtons. So that would be Bob's weight on Earth in newtons. Now, in some areas of the world, like America, you don't use newtons for your weight. They have a unit called pounds, and here is the conversion. 1 pound is equal to 4.448 newtons. Now, this is an actual conversion because pounds and newtons both represent the same variable. They're both forces. So if I take the 686 newtons, I will convert this newtons at the bottom to pounds. 1 pound, 4.448 newtons, and I will get 154 pounds. So on Earth, someone who has a mass of 70 kilograms will weigh 154 pounds. However, what happens if I bring that person to the moon? Well, the force of the moon on Bob would be 70 kilograms times 1.6 newtons per kilogram. Again, kilograms cancels. I would get 112 newtons. So if I convert this from newtons to pounds, newtons cancels, and I would get 25.2 pounds. So a person who weighs 154 pounds on Earth would weigh approximately 25.2 pounds on the moon, but their mass does not change. Let's take this idea and let's actually do it in reverse. So I have another person. Let's say that this person has a weight. Now, weight is force Earth on object. Let's say they weigh 125 pounds. So the question here is, what is their mass? Well, I'm going to take the relationship we had before because force Earth on object is mg. And again, force Earth on object, this is weight. However, due to the units here, we need to get this weight in newtons and not pounds. So I'm going to do 125 pounds to newtons, 1 pound, 4.448 newtons. So I'm going the other way this time. Pounds cancels, and I get 556 newtons. So if I did a force diagram of a little person here, I would have force Earth on person is 556 newtons. If they're standing on flat level ground, then I would have force normal on person would be 556 newtons as well, if they are not going anywhere. When you are creating a force diagram, as long as the problem is on Earth, the first force you are probably going to find is force Earth, especially if you're given the mass, because literally all you have to do is this. Now, in order to get their mass, I would then use this relationship. I'm rearranging force Earth on object over G for Earth, and I would get 556 newtons divided by 9.8 newtons per kilogram. This is a fraction of the denominator. This flips, newtons cancels. My answer comes out to kilograms. And this person would have a mass of 56.7 kilograms. And then I can work with it from there. So, big takeaways. Mass and weight are not the same thing, but they have a relationship. Mass units, SI, are kilograms. Weight unit, SI, is newtons because it's a force. The weight unit you are maybe familiar with, depending on what country you live in, you may be familiar with pounds. Now, if I ask which of these do not belong, it'd be kilograms, because kilograms is a mass. Newtons and pounds, these are both forces. This is a mass. So when someone asks for a conversion between kilograms and pounds, the assumption is that we're on Earth, which is quite honestly a fair assumption to make because most of us are never going to leave it. However, technically, there's no conversion between kilograms and pounds. If you notice, I went from pounds, first I went to newtons because that is a conversion. Then, depending on where we're located, the ratio between how much the planet is pulling with, depending on how much mass an object has, can change. Most of the time, you'll be using G, because most of your problems are going to be on the surface of the Earth. However, if an assessment really wants to know if you understand this concept, they will literally change what planet the problem is on. They could put it on the moon, they could put it on Mars, and how you get the different ratios on the planets is something we're going to discuss in a later topic. Side note, the farther away you get from the surface of the Earth, the lower this number actually gets. So you wouldn't just have a different weight if you went to the moon. If you climb the top of a very tall mountain, technically this number would decrease and your weight would be lower than it would be at sea level. However, your mass would still be the same. That is my lecture on the difference between mass and weight. I hope it has helped you out. Have a good day. This is Mr. M signing off.